Optimize. A journey through database query optimization. This course is filmed on location at Carnegie Mellon University in front of a live studio audience.
I'll post this in Piazza as well. But we've already gotten 2 emails from Google and Amazon because they know the courses exist. They know the course exists. They want to know who's taking the course because they want to hire you already. So we'll do what we did last semester, and we'll have a spreadsheet. You know, if you want to talk to companies, a bunch of people are going to hang out with Larry Ellison, like, so you're not, you're making a face. That what? You're going to hang out with Larry Ellison?
I'm not.
You're going to Oracle. Yeah. It's about the same, right? I mean, you know. No, so we'll do the same thing. If we'll put up a spreadsheet, and if you're looking for either full-time or internship, or even internships, one of them said it's an internships for this summer, so that would surprise me. Anyway, yeah. So if you're interested in talking to them, then we'll put your name in the spreadsheet. And then if you're doing internship this summer and you can be out in California, while you're out there, you might as well go interview with them, right? It's always good to have competing offers. And again, there's not another course in the US that I'm aware of that teaches query optimization. And they're always looking for someone to do query optimization. But there's 2 other courses in the world that I know are doing query optimization. They're all from the Germans.
Is this BigQuery and Redshift?
Redshift, yes. Companies are emailing about hiring students taking this class already. Yeah, it was BigQuery. Yeah, no, AlloyDB. Sorry. Yeah, which is when is February 5th? Oh, that's today. Oh, all right. Take that. Sorry, I got just like an hour ago or 50 minutes ago. I just got an email from AlloyDB wants to hire you guys. Hold on, there's another one. There's another Google one. It might be BigQuery, it might be Bigtable. I forget. And again, this part, right? So you should get paid a lot. All right. So today, again, last class we were talking about the progression of where we're going in the course. So today was the our initial jump in and discussing in more detail how to do join enumeration and join ordering. So again, the paper I had you guys read was from the Germans. How did everyone do with that one? It's okay, right? Because that one's probably the most accessible one of all the Germans for query optimization, right? Now he's sort of name dropping a bunch of algorithms. We'll go through them as much as I can. But the other ones, like the dynamic hypergraph one, the dynamic programming hypergraph one, like that one, he goes hard in the paint, the theory. Whereas this one, again, it's a lot. And we'll try to cover as much as we can, but it's in my opinion, it's most accessible, and it's, to me, it's a brilliant idea. Or the suite of ideas he's throwing at the problem are brilliant. All right, so again, as I said last class, we were stepping off from the sort of or jumping off the ground from this, now understanding the foundation of what a query optimizer is going to look like. Again, whether it's top down or bottoms up, and now we're starting to go in more detail about how you're actually going to implement the different pieces of the optimizer you need to actually generate query plans. So last class was focusing on transformation rules, right? And the idea here is that there are heuristics or that you could apply to transform the query plan into one form to another, and then you're sort of pushing things along towards ending up with the final physical plan you actually execute, or moving the plan to a sort of point in the search space that is amenable or is open to more additional optimization rules you can apply. So we talked about how to do access path selection with a single access path and multiple access paths, inner joins, outer joins. Outer joins we'll see more again next class. We'll talk a little bit about today, but outer joins are complicated because they're not always commutative or associative in the same way that inner joins are. Group bys, and then special case for star and snowflake queries as well. Okay? All right, so again, today's class, now we're gonna go more detailed, like, okay, so yes, transformation rules, we know how to swap things from left and right from based on commutativity and associativity rules. The next question is, okay, how do we actually start looking at the different possible join orderings in an intelligent way so that we're just not falling back into doing an exhaustive search, Like as we said, like it's an NP hard problem to select the right join order, so we can't just enumerate everything. And I made the comment last class also too, is like, well, the good news is that for a lot of queries, most of them don't do any joins, right? Most of them are single table queries, right? And we still have to do some challenges to those, right? But we don't have to do the join enumeration. And then when joins do arrive, when we see queries that do have joins, well, the good news is that most of them are going to be 2 tables, right? Most of them are not going to be the 5001 he mentioned, right, in the paper. So, all right, for those cases, we can do action exhaustive search. Like that'll be good enough. We'll find the optimal join ordering, right? And I was trying to find this graph. I know I've seen it in either a paper or some presentation at some point, but I wanted to show a graph that basically, if you look at a sort of as a collection of queries in real customer, real database workloads, you would sort of see a power law of like, for the queries that do have joins, they're all going to be mostly 2 table joins, and then 3 tables maybe half as much, 4 tables half as much. Right? It's an exponential curve, right, of the number of tables you have to join a table. So for the ones that are for the most common case, we'll be able to handle those just fine because we'd run those do an optimal search, right? It's the things with the outliers, right, that we have to deal with, and those are going to cause a bunch of problems for us. Because again, as we know, picking the wrong join order can have orders of magnitude difference in performance. And so now if you're talking, I'm doing a 100 table join, which exists, the result of picking a bad joiner is catastrophic, right? And so in the paper he mentions that like, oh yeah, like there's a bunch of citations where people have done analysis through SAP and Tableau. Tableau was bought Hyper, which is the first data system that the German built, Thomas Neumann. So they actually had access to real workloads. And they said, oh yeah, there's oftentimes you see real queries written with hundreds or even thousands of tables. And the largest known query that's been publicly disclosed that people talk about is this one behemoth from SAP where they were doing a 5,000 table join. And clearly this is not written by a human, right? This is all generated through some dashboard, right? People clicking things. It's a machine generated query, but these things certainly do exist. They're rare, but they do exist. And so I've seen at a private event, I've seen the schema of the one SAP customer that had this particular query. And I thought I took a photo of it. The best I could find was this thing here. So this is just showing you what a stable query looks like. And the details are not important, but I just want to point out here, it's declaring a view. So in SAP, their enterprise software, you pay a lot of money for it, right? The reason why SAP is a huge company, right? It's views upon views upon views upon views. You're building views on top of other views. And inside of all those views, you're doing a bunch of joins. So one query may show up, and even though it may reference like a single table or a single view, that thing balloons out, and it's this massive dependency tree of all these joins you have to do, right? So this is just one example of something nasty that come your way in real workloads, right? So when we build our optimizer, we obviously want to be able to handle the common case, the easy queries, and we'll define what we mean by easy in a few more slides. But when these behemoth queries show up, we don't want to fall apart and just give up or have horribly terrible plans that are no better than random, right? We still want to be able to handle them. And then one of the key insights that comes out of this paper is that they recognize that you actually do need different strategies based on the complexity of the query. And so that, again, for the easy ones, you can do optimally. For the medium ones, you can do a little bit better than just blindly jumping into your dynamic programming algorithm. You sort of set things up to simplify the problem, like at least with having a good starting point. And then for the large queries, it's going to be a bit random, but you can be a bit intelligent at what your random start looks like. And then you start sort of tackling the sub-problems in the query plan, right? So today we're going to spend most of the time going over the paper you guys are assigned reading, the adaptive join optimization from the Germans. And again, as I said, they name drop a lot of different algorithms and different methods. It's a very thorough related work section. And I can't cover everything that he mentions, but I'll try to go through the most important ones. Okay? And then I'll finish off briefly talking about randomized algorithms just because I think they're kind of interesting. They're useless for what we want to do in a real system. But we'll look at 3 different variations of this because that's one of the ones that showed up in the paper Actually, he had 2 randomized algorithms that he compared against. Okay. All right. So as I said, the key insight of this paper is that instead of your optimizer just having a single search strategy to do join enumeration for all possible queries that ever show up, that you're better off selecting a algorithm that is best designed to handle the complexity, or the logical complexity of that query. And so that for the smaller ones, or the more simple ones, you can provably find the optimal query plan. But then as things scale up, things, you have to sort of switch your strategy. And so for the small, medium queries, they're going to do a combination of a dynamic programming approach that'll be sort of similar to the system R1, but actually a more advanced version of this that's going to be based on hypergraphs, we'll quickly talk about, and then we'll see again next class. So you do that for the small, medium queries. But then for the larger queries, you want to degrade the quality of the plan gracefully, because it's just impossible to find the optimal query plan. And so you have a sort of a way to say, I'll spend a little bit more time trying to sort of set things up, or maybe target the things that are the worst part of my query plan, and then just run with it. So the decision tree for how this is going to work in your optimizer is that SQL query shows up, and then there'll be a mechanism to identify, do we think the complexity of this query is small? Right? There's a simple thing could be the number of relations you see in the query, but as we'll talk about in a second, like that's not going to be sufficient, because it's actually the structure of the query that matters. So complexity is some logical complexity, not necessarily like how much data you're actually going to read. Right? It's more about the structure of the query plan. So if you identify that it's small, then they're going to solve optimally using a dynamic programming algorithm. Right? It could be the system R1 we saw before. But they're going to do a variation of this. If it's not small, then you check to see whether it falls under the scope of being medium. If yes, then you're going to do another dynamic programming approach, basically the same one as the first one, but you're going to simplify the problem by converting the graph structure of the query plan into a linear chain, right? So again, you can't prove you're going to be able to solve this optimally, but because you put things into a more simplified form, you're going to do better than just trying to tackle the whole problem in itself, right? So you're making some assumptions about what the query plan is going to look like, again, without violating any constraints you may have that in how things can be joined, but you simplify the problem and solve that one. And then if it's still too big to be medium, then you fall back again to this greediness approach, where you sort of start off with a greedy search, generate something, and then again you do more targeted refinement based on the worst parts of the query plan. All right, so as I just said, the logical complexity of this query isn't based on how much data you're actually going to read, right? Their algorithm doesn't care whether you're reading 1 billion tuples or 10 tuples. It really comes down to be what is the structure of the query plan itself, right? And it can't just be because you're going to count the number of your relations you're going to access, because again, if all the relations are joining with each other, then that's more complex than a chain, right? So it's the relationships between the relations in how they're going to be joined together that matters. So there's a bunch of different categories of query graph structures, but I want to focus on the two extremes. And in actuality, most of the query is going to be somewhere in between, like the star schema stuff that we talked about last class. That's going to sort of be in between the two of these, right? So the most simple most simple query graph structure you can have is called a chain graph. And this is where each relation is going to be connected to at most 2 other relations. And it's going to find the linear ordering of the in which you need to do the join. So it looks like an example. So I have a query here that I'm going to join 4 tables: R1, R2, R3, R4. But the way the join clause, the predicates are set up, is that I'm going to join R1 and R2 on the RID. And then R2 can either join with R1 or R3. R3 can either join with R2 or R4, and R4 can only join with R3, right? And because I know I'm going to want to throw away Cartesian products or cross joins, then I don't need to even bother looking at whether I want to join R4 with R1, right? Which again would be valid. We throw things away, assuming these are all inner joins. But if we have we see this structure here, we basically know the order in which things need to be applied in relation to the other tables, right? So again, this is the best case scenario, right? Because you sort of think the number of edges in the graph is minimal, right? To have a connected graph. The other extreme is called a click graph or clique graph, and this is where every relation can be joined or is connected to each other, connected to all other relations in the query graph, right? And it'd be something like this, where again joining 4 tables, but now I'm going to have join predicates that for every relation I'll have some match up with the ID field in every other relation, right? So this is kind of bizarre. Like, who would ever actually write this? They do exist, and oftentimes maybe you don't see like the entire graph be the clique, or sorry, the entire query represent the entire clique, but like a subgraph of the total query plan could look like this, right? So the idea is that, again, when a query shows up, we're gonna generate this join graph here, which is easy to do. You just look at the predicates and understand how the relations are connecting to each other, and then based on that, we'll then determine which of those 3 categories of complexity classes that the query will be in. And again, just going back to what I said before, like again, the star schema stuff, like you can sort of see how like the fact table would be in the middle here, and it would connect out to all the dimension tables, but like the dimension tables would not connect with each other. So it's more complex than the chain graph, but it's less complex than a clique. So what's going to happen also too is that when they set this up, you're basically putting entries into instead of a memo table, it's the DP table for the dynamic programming table. Like, you're going to set up, here's the entries of the things I need to explore when I'm about to do my join enumeration. And it's the number of entries that you're going to see in that table that's going to correspond again to the complexity. So for small queries, if you recognize that when you populate that DP table, if there's 10,000 or less entries, then you know the graph is considered simple or small, and therefore you can use the optimal search algorithm, right? So if it's a chain graph, you can have up to 10,000 relations, 1,000 relations all linked together, and that'll be roughly correspond to 10,000 entries. But for cliques, they can only go up to 14 relations. Again, just because of all the dependencies between all the different combinations of the joins, right? If you go beyond 14, it explodes the size of the table. Right? All right, so if we recognize that our query is small, then we're going to use this dynamic hypergraph, dynamic programming hypergraph algorithm, I'll talk about in a second, to generate the optimal ordering. And the idea here is that it's going to be able to enumerate all possible join orders exhaustively, so it's guaranteed to find the optimal query plan, and it doesn't have to look at redundant things in the same way that the System-R approach did. So the key difference between this approach, the dynamic programming hypergraph one, and from the System-R one, is that in the System-R one, they were getting just sort of enumerating all possible join combinations and sort of exploring the entire graph structure. And the key insight with this newer algorithm, which is also developed by the Germans, so this was developed by the same guy that wrote the paper that you guys read for today's assigned reading, and with his PhD advisor. So this is after he graduated with his PhD, before he started at Munich. So the idea here is that instead of modeling the queries just all possible just combinations in this giant graph, instead, if you can model things as hypergraphs, where you recognize that there's some connected subgraph within your join graph, and instead of looking at all the possible join orders individually for the elements or the nodes within that hypergraph, if you just treat that as like that grouping as a single unit, and then you don't need to explore everything inside of it all at once. So the idea is that you're going to generate a bunch of these subgraphs, and then you'll connect them together with what they call hyperedges. and then you will incrementally add edges between the other nodes to eventually have a complete connected graph that you can run as the join algorithm. And then you can sort of within each subgraph or within subgraph, you can then figure out the optimal ordering of that. And we rely on that principle of optimality we talked about before, where if the subplan is optimal, then it has to be, by definition, part of the global optimal plan. So again, it's a divide and conquer approach, but when they do enumeration, because you're representing the query as these with these hyper edges, you don't have to look at every single one individually. The same with that system R did. I'll briefly show an example. So this is the approach he first developed, again, back in 2008. He implemented this in Hyper, which is what Tableau bought. Umbra was the system that, well, they didn't mention Umbra, I think, in this paper, but that's the system he was running on for the paper you guys read. So this is the successor to Hyper. The DuckDB guys basically took this paper and re-implemented the same thing. I don't think they implemented the stuff we talked about today, this adaptivity piece, but they certainly implemented this hypergraph search. And then GlareDB is a new data system out of Texas where they started off using data fusion and then they threw it all away. And the guy claims he's rewriting it based on this algorithm here. But I don't think it's public yet. At least the source code isn't public. All right, so again, what are these hypergraphs? The idea is that it's a grouping of nodes that are being joined together in some way. And then now when I want to represent that I'm going to be able to do a join between two different groups, I would represent them through this hyper edge. So again, now as I'm doing my enumeration, looking at all possible query join orderings, I don't need to consider R1, R2, R3 individually with R4, or R5, R5, and R6. I can just say, let me optimize this subgraph first. Let me optimize this other subgraph first. And then now for all the possible hyper edges between the different subgraphs, figure out the right join ordering of those things. Right? Again, it's a divide and conquer approach similar to System R, but again, the idea is that we're grouping things more intelligently based on what we know how the query wants to join the tables, rather than blindly just looking at all possible combinations. So I've already said this. I'll just say it again. And the idea is you traverse the graph in a fixed order and recursively go into to different subgraphs and join larger ones. And then you only have to consider the ones that are connected. Sorry. Then you start connecting the larger subgraphs with each other through these hyper edges, and then you eventually end up with a complete query plan. I forget the complexity of this. I think, but it's less than the system R1. The other thing that this also can handle is that it can handle complex join predicates, non-inner joins, cross-product joins, right? It does a bunch more things more efficiently than what the system R did. So we'll see this overall approach next class. I'm going to rush through it because I want to get through all the other ones. But this will be the backbone for what they're going to do for small queries and medium queries. So small queries, you run this thing to its completion. It produces the provably optimal query plan. And then for medium queries, we'll see in the next slide, they'll contort the query plan into a form to get it something that this makes the problem more tractable inside this. Any questions about small queries? Yes?
On hypergraphs defined as, or hyper edges at least defined in general in computer science as edges where there are multiple nodes being connected together in one edge. Isn't that the definition of hyper?
Yeah, so like, it's basically, yeah, so like R1, R2, R3 connected with all the other ones. So represent, instead of individual edges, it's just one edge.
Over here, is the edge indicating a join? It's a simple edge. Is that indicating a join? If so, why is the query like that? Because the query says R1.A plus R2.B. That doesn't indicate there's a join between R1 and R2. That just indicates that we need to consider both those.
You need to join them.
You have to mash them up in order to do the.
So the query is slightly incomplete.
No, it's like a cross product.
That's a cross product, right?
Yeah, which is still a join.
Yeah, okay, yeah.
Just one question on this. Will we get the most optimal plan for this? I don't think so. Right?
Yes, this one you do. Yes.
You do, it's just like for different shape of the plan, it can get quite expensive, but if you only have a chain, I think it ends with
Yes, that's it.
I know that about the NQ part.
Yes.
I was like confused about, like, because let's say if we just try to check for like each one of them it joins each other, right? Then that will have, because this can miss out some scenarios is what I felt, but I'm not very sure.
So in the paper, it doesn't describe how they handle cross product joins and outer joins. That's in another presentation. He gave a presentation on how to handle that in this as well. Let's skip that for now. But to his point, he's correct. Like if you let this run forever, it'll find the optimal query plan, right? And so the idea is that they don't want to let it run forever, right? So they instead of like letting it run like, oh, you're going too long, what they're instead going to do is they're going to recognize by doing the categorization of the complexity of the query before you start running it, then you have some reasonable guarantees that it's going to finish in a certain amount of time. And for the ones that don't fit this categorization or fit the limitations of a small query, they're going to set up they're going to change the query graph so that when you feed it into this algorithm, it then can actually then finish. Because as he said, the chain queries will finish, the cliques won't in a reasonable amount of time. Okay. So with that, let's talk about how they actually do that, right? So if they say you have, for a query with more than 10 relations, then the goal is going to be to try to convert the query into a chain query, as I showed before, because this is going to greatly simplify the problem. Because again, if you reduce the number of edges you have between relations, then there's fewer, there's fewer possible joint enumerations you have to consider. So again, the magic is going to be how do you actually then convert any arbitrary query plan into a chain query. So this is going to be through the technique they call the search space linearization, and this sort of flattening the arbitrary query graph into a chain query. And so when this happens now, then we only need to consider the associativity rules of doing those transformations and not commutativity, because now we know that you can't, you're not going to swap things around. Or you don't want to consider swapping around because that's going to explode the search space. So you're reducing the number of possible enumerations you have to the enumerations you're considering by simplifying the problem, but you'll at least be you'll be close to the near optimal, but you can't prove it. All right, so how are they going to flatten things down? So the idea here is that again, if you know the order. Sorry, the way this is going to work is that you're going to have some kind of oracle tell you, here's the optimal ordering of the relations for joins. I'm not going to explain how they do that just yet. Just assume that someone's going to tell you at the very beginning, here's the optimal ordering you should use. And then now what you do is, once you have that, then you're just going to do a DP algorithm where you'll look at progressively larger size of join sets in the query plan, and then start building up the query plan. So the idea is that at the very beginning, I'm just going to look at just combination of two relations. And again, the order in which I want to execute my joins is going to start from here to there. So I know I need to join R2 with something first before I join it with join something with R6 and R4, right? So I'm going to look at can I join R2 and R1? I look up at my graph up above. Yes, there's an edge between R2 and R1, so I know I can join them. Then now I go to R1 and R3. I recognize that there's no edge connecting R1 and R3, so I can skip that. If you want to support cross-product joins or Cartesian products, you could then add that kind of edge, that connect. You would add that here. For simplified things, we're going to skip that.
Doesn't add R2 and R3 right after it checks R1, R3, then checks R2, R3, right? And then adds the R2, R3?
Yeah, you're right. Yes, it does that too. Yes. Yeah, so yeah, the animation is wrong. So instead of sliding along here, you would look at R2 and R3, R2 and R5, R6, right? I'll just simplify it this way. All right, so then we do R5 and R6, we have an edge there, we connect those, R6 and R4, we skip. So then now we look at progressively larger ones, and as they said, it would be R2 and R1, R3, R2, R1, R5, and so forth, right? But again, the key thing is that you're always sort of going in this order, and you want to try to joining this before anything else, right? So in this case here, the output R2 and R1 from up above has an edge between R2 and R3, so therefore we know we could have a join between those, right? skipping this all the way down, we get to R3, R5, and R6. If we join, if we take the output of R2, R1, and R3, we can then join that with the output of R5 and R6 because in the output of this three-way join here, we would have the R2 values we need to then join it with R5. So we then add it to that, and then to get the end, we add R4 like this, right? So again, we're sort of starting from this side here, adding up the query, adding up the joins, going from left to right until we produce the full query plan. And so the key thing about this is one, that we can actually generate bushy plans here, whereas in System R, they threw away all the bushy plans and only consider left deep join trees. And then the other key thing is like, well, I said that some magic oracle is going to tell us how we get this ordering, because that's going to influence how we're going to build out the join tree. So the question is, how are we going to do this? Yes?
So the join order means that the scan order that we are going to build this tree, not the actual, like, the order we're going to join and two things together.
His question is, what do I mean by optimal join order? It just means that, like, as I build the tree, I want to make sure I join R2 with something else before I try to join R4. If I'm allowed to, according to my graph, right? If I'm allowing Cartesian products, cross joins, then I can join R2 with anything I want. But to simplify the problem, we're not doing that. We only do inner joins, right? So again, in this case here, we have this query plan here. The database system could decide, that I wanted to execute the join on R5 and R6 first, then execute R2 and R1, right? It's sort of a runtime decision it can make. But from the query plan itself, the idea is that, like, this would be at the leaf nodes here. I mean, R5 and R6 are as well, but the output, the system could then decide, I don't want to join these because I know I have to join it with the output of this. And depending on how I slice up the query plan with pipelines, I may want to delay executing that. But so R2 is very likely to get run first, or the scan on R2 would get run first. Okay. So Thomas loves finding papers from the 1980s that have very few citations, but solves exactly the problem he needs. So here's another one that he pulled out. I forget this. I think the number of citations is like 60. There's one paper when he does MVCC that does precision locking. He found this paper from like 1983 that literally had like 20 citations, and it had solved the exact problem that he wanted. Oh, it's amazing. All right, so the way he's going to generate the optimal join order is he's going to approximate it by using this algorithm from the 1980s that will generate the optimal left deep plan for a tree in n squared time, so in polynomial time. So the idea is that instead of doing a more expensive algorithm to figure out what is the true optimal ordering, he's going to figure out what the optimal ordering should be for a left deep tree, run that in very quickly, and it produces a reasonably good result, and then have that be like the starting point of how he's going to start looking at deciding to generate the rest of the query plan tree. Right. So the basic idea is that you're going to, in this algorithm, you basically take the query graph again with these join orders, or sorry, with the joins, and then you're going to transform it into a precedence graph that'll define some linear order in which you have to generate the query plans or do the joins. If the graph has cycles, then you just run the minimum span tree algorithm to convert it into an acyclic graph, acyclic tree. And you make decisions on which edges to include based on the like choosing the most selective edge, right? Because the most selective predicate is going to throw away as many more tuples than anything else. So I want to keep that around. So then now I'm going to assign a rank for all the nodes. That's going to be a combination of what its selectivity is divided by the cost of actually executing it. So it's basically a cost benefit ratio. And then now I'm going to successfully merge child chains together according to the ranks, and make sure that I'm keeping things in the right order, so that I'm choosing nodes in the order of my initial join order that are going to be essentially have the most benefit, be most selective and the least overall cost. Choose those first, and then whenever I have a conflict where something is logically required to be joined after something else, but the rank ordering says I want it to be above the other one, I'll just combine them together. So let's look at an example. As I also say too, I think the original idea came from this 84 paper in Todd's, which is the sort of theory conference, and then I think the VLB 1986 paper is the actual. I don't know. I forget whether I should check whether they cited each other, but like here's the actual implementation of doing this. And again, this is like in the 1980s. Everyone was sort of trying to come up with different algorithms to not have to do the SysMar style exhaustive search or the DP search that they were doing. So this is again a way to approximate what would be, or to come up with what would be the optimal join ordering for a left deep tree without having to solve the overall join ordering problem. And so Thomas is using this in his approach to, again, provide a good starting ground for the join ordering, because then he can run a more expensive DP algorithm to find bushy plans and other things. All right, so the way it's going to work is that we're going to build a precedence graph for each individual relation that we have in our query plan, right? And you have to build a precedence graph rooted at every single relation. So if you say this is for the one for a precedence graph for a query rooted at A, it would look like this. But then you would have ones for rooted at B, C, D, and so forth, right? And then there's no logic here. There's no cost calculation. It's literally just saying in what order something has to be joined with something else. Right? In my example here, I'm going left to right. So then for each of these graphs, we'll pick the one rooted at A. We're then going to generate the sort of the sequence of the join orders, and then for each of the nodes representing the relations, it'll be that cost benefit ratio. So what's the selectivity of the selectivity of the predicate that might join, and what's the cost of executing that query, or sorry, that join operator, or based on like the number of tuples I expect to actually have to read in for each relation. And then what happens is, if you recognize that going from top to the bottom, that you have two nodes where the rank is actually it doesn't follow from lowest to highest, right? So 3/10, that's a lower cost than 4/10, but 3/10 down here, this is less than this. So in my graph structure, I actually want to join this before this, but logically I can't because of my edges up above where I have to join E with F, and I can't join F with anything else. Otherwise, and again, end up with a cross product. So when this occurs, they just combine it together into a single node and then sum together the two costs like that. So you end up with 7/10 like this. And then now I'm just going to go from the top to the bottom and merge chains based on increasing the rank until I end up with a linear form like this, or a chain query like this. So that's how they're going to approximate what should be the initial join ordering, and this is probably going to be the optimal join order only for a left deep tree. Yes.
Where are they getting the initial rank values from?
The rank, so it's the selectivity is the numerator, and then the denominator would be like the number of tuples I have to read for that relation, right? Which you would have because again it's in the optimizer. So again, this is an old algorithm. I don't think, well, actually, it's an old algorithm. This is probably what a lot of people, when they build a first query optimizer, will basically implement something like this, right? Because you don't have to do deep call search or DP search. It's just like it's applying heuristics to generate this thing. All right, so again, for medium queries, we're going to first linearize the graph using the IKKBZ algorithm. And then from that linearization, we know we have now an upper bound on our query plan cost. Because, again, it's a provably optimal left deep join tree. So any other query plan we're going to pick will have to be better than that. So we're basically now looking for a bushy plan that's going to be better than that, than the left deep one. But if we don't find it, then we at least have that left deep one. So again, it's a good starting point for us. we can run it efficiently, and if we use the remaining time to then actually look for, to do the DP algorithm to refine it and try something better. Again, it's n cubed, so that's fine for, I think for 100 queries it does okay. Beyond that, it explodes, and things get worse, right? It's not as bad as exponential because it's polynomial, but still not great. And if the goal again, if it's able to find a decent linearization, then it may then be able to uncover the global optimal Bushy plan. It's not guaranteed, but it's could be close. All right, so that's small. We've done medium. Now the question is, how are we going to handle the larges, right? So for this, they're going to use a technique where we're going to rely on a greedy algorithm to generate an initial query plan, and then they're going to identify portions of the query plan of size k, with k relations, and they're going to target the ones that are the most expensive, and then run the DP algorithm to optimize those for some amount of time. Put it back in the query plan, and then go find the next most expensive subgraph and optimize that, and keep doing that till you run out of time. So the key thing to point out, though, is that in the original paper, I think from 2000, that describes using this technique, they talked about having subgraphs of, I think, 4 to 7 relations. Like that was their ideal case. But if they do that same linearization trick we just talked about before, to again simplify the problem before you feed it into the DP algorithm, right? They can say we can get to be k equals 100 and still produce pretty good results in good time. So there's a bunch of different greedy algorithms you can use. I want to focus on the greedy operator ordering because it's the most simple one. There's also minimum selectivity. It's basically you're just picking whatever edges have the minimum selectivity one, right? We'll see something similar in the QuickPick algorithm in a second. All right, so this GU algorithm goes back from late 90s. So again, you kind of see, like, I gave you guys a paper that you guys were all born since you were born, and then keep falling back to older ones because a lot of these techniques he finds are the core foundation of a lot of these optimizer techniques goes back to the 80s and 90s. All right, so the idea is that we had this query graph, again, with connect between edges based on joins. And we're going to find a pair of connected nodes, I and j, that have the minimum value for this formula here. So it's going to be the size of the tuples that are being fed into each of these nodes, each relation, multiplied by the selectivity of the predicate in the join clause for those two relations. So you can think of like some approximate numbers for these 4 relations, A, B, C, and D. Here's the size of the data, or the number of tuples that they're going to generate. And then for the edges, there were some estimates on the selectivity. So again, what we want to do is we want to look at all possible combinations of nodes in this graph, and then run this formula on them, right? And I'm actually missing. But they have to be connected, right? So the reason why I have A, B, B, C, and D, D, and not like AD or AC, because again, there's no edge between them. If I'm not considering Cartesian products, then I don't want to do that, right? So this is pretty easy to do, right? Again, just do this math here, and then now what I'm going to do, I'm going to pick the one that has the lowest cost, the minimum value of all of the 3 choices that I have here, and then I'm going to merge those nodes together, right? And then in the new graph that I'm going to generate, I'm going to have this new node of the merged nodes from the original one, and I'm going to set the size of the node to be whatever I've calculated for this formula here, because that's again determining the number of tuples that are going to come out of this thing. So implicitly, I'm saying I've done the join, say on B and C here. Look at the graph. I've done the join in B, C here, and then when I'm emitting, what I'm spitting out now is 2,000 tuples. And then now you got to go back to all the other edges that are connected to the edge, to the 2 nodes that you merged together, and you update now their selectivity to say, okay, well, if I do my join predicate on my original relation A, but now on the output of the join of BC, what is the selectivity of that predicate going to be? It'll be very wrong. It's hard to calculate these things, as we'll see later on, but like it's the way the formula works, the algorithm works. And then now recursively keep doing the same thing over and over again until I run out of nodes, only one's left, right? So again, for the two connected edges, A and BC and BC and D, I just run that same formula. I would then pick this one near the lowest cost. So I would end up merging A, B, C together. I would then, again, in the next round, I would then merge it with D. And then I would end up with essentially the join order that looks like this, right? And so my example here, because it's, the graph up above is sort of simple, I ended up with a left deep join tree, but this algorithm would still work to generate bushy plans as well, right? If I had maybe like an edge between C and D, I could have ended up joining C and D first and had that be one side of the join tree and then join B and C and A on the other side, right? For this example, I just ended up landing on left deep tree. But the whole point of this is not to only consider left deep trees in the same way we did for the other linearization technique. All right, so again, this is going to work with both cyclic and acyclic query graphs. And then again, not just left deep join trees, it can generate the bushy ones as well. So then now you have this, you have this first approximation of what the query plan is going to be, right? And this is a pretty simple algorithm to run. And then now you're going to go through and target the connected subgraphs and how you identify what's a connected subgraph and so forth. Right? That's a bit more complicated. But you identify the subgraphs, then run the DP optimization algorithm on that subgraph. And thinking of like with the hyper edges, you're trying to say like, okay, here's this piece of the query plan that is connected to other things, and I don't need to worry about how they're being connected to other things. I'm just worried about how to optimize within that small region. Run DP on that, and then for a certain amount of time, and then stop that and go choose the next subgraph to optimize until you run out of time. So again, this algorithm runs in n cube time, which again, it's reasonable. And for really large graphs, it's really large query plans, there really isn't an alternative. All right, so I know there's a lot of tables and a lot of in the appendix and the paper. I'm just going to focus on one graph he had where he's comparing the how well his system, his adaptive approach can handle increasingly large queries with increasingly larger number of relations compared against two commercial systems, Oracle and SQL Server and Postgres. And so I should have maybe include the performance numbers for his own system because he compared them with different algorithms, so like how good the query plans are actually at runtime. But for this, we're going to say how fast is the query optimizer compared to these other ones. So in case of Oracle, within I think the first 50 relations just shoots to the roof, and in some cases I don't think it even completes more than 100 queries, 100 relations. For SQL Server, it starts balloons over 300. In Postgres, we'll talk about it in a second, they're actually going to use a randomized algorithm that is based on time. So you basically say, I'm going to let my randomized algorithm run for a bit, and then when I run out of time to stop. But because all the internal data structures for how they set up keeping track of what these relations are and in the query plan itself, that end up becoming the bottleneck. So after 700 queries, you're just blocked on setting up all that metadata or infrastructure about the query plan before you can then feed it into the randomized algorithm. And then that's where everything falls apart for them. And then for them, for the Umbra, for the adaptive approach, right, they're completing things in 500 milliseconds, which is impressive. And the query plans are reasonably good.
Within 10%, I think.
Yeah, within 10%, yes, which is very impressive. Okay. So I want to briefly talk about another category of algorithms that he mentioned a bunch of different ones. And again, the idea here is it's a smorgasbord of like, here's a bunch of different approaches to how to do this. The Umbra guys are putting everything together, but it's kind of good to know what else is out there. And then we'll see more of these again next class on Monday. All right, so all the things we talked about today, assume everything's inner joins and no cross products. Of course, we talked about before how outer joins, you want to be able to include them. And I don't think this paper talks about it, but he has other work that talks about it. Like in some cases, the cross product join actually is the best thing to do. When tables are sufficiently small, like tens of tuples, the Cartesian product is actually going to be the best choice rather than an inner join. And of course, you don't want to just blindly include Cartesian products in all your possible joint selection algorithms, because if you have two massive tables, cross joining would be a terrible idea. So they have some additional heuristics to say, if I recognize that these tables are really, really small, then maybe I do want to consider doing a Cartesian product on it. But I don't think they go beyond the roots or the bottoms of the query plan. So like once you get higher in the query plan, because the cost estimates will be way off, you definitely don't want to be doing Cartesian products. So they skip all that. So we'll talk a little bit more about that next class as well. All right, so I want to bring up now these randomized algorithms because they showed up in the paper, and again, they're interesting, or at least worth considering. There's only one data system that actually does this. I've already said what it is, Postgres, right? And it's actually terrible, and it's advised not to use it. But they don't really have, again, their joint enumeration algorithm is not very good relative to certainly SQL Server and other things, right? All right, so if you have a really large query of a huge search space, one approach is to flip a coin, do a random walk on the solution space, keep track of the best query plan you've ever seen so far, and then if you magically stumble upon a new one that's even better, then absolutely go ahead and just use it, right? Random is actually surprisingly good, right? A lot of times when you see these LLMs are different beasts now, but like these, a lot of times these optimization algorithms or Bayesian optimization techniques, where they're using heavyweight machine learning methods, a random walk does surprisingly well. And so it makes sense. You want to apply this for database systems. So the three algorithms that I think they were mentioned in the paper, and I compare against the Postgres one and this QuickPick one. So the way QuickPick works is you have this set of all the edges between in your join graph. You randomly pick one, remove that from the sort of the edge set, and then add the join of the two relations represented or connected together by that edge in your query plan. Check whatever the current cost is of that query plan, right? And if it's worse than the best query plan you've ever seen before, assuming you start with infinity, then you just throw it away and start with a random set and reset everything and start all over again. But if it is still less than the best cost we've seen before, then you randomly pick another edge and join that. And then you just keep doing this until you run out of time, right? And it in some cases it works okay, right? And instead of doing sort of random sampling or uniform sampling from the edge set, you actually can bias the sampling function to be based on, to try to choose the edges that have better selectivity, right? So that you, again, end up choosing joins where you know you're going to throw away more tuples earlier than the query plan and other ones. Yes?
What about explainability?
In terms of what?
You never be able to explain your own query plans.
So I mean, you can explain the query. You can his statement is, what about explainability? There's explainability of the query plan, explainability of the algorithm. If I run explain and I get this, it'll tell me what the query plan looks like. But how do they find it? It's random.
You can't recreate it.
Well, hold on, we'll talk about that in a second. So he said you can't recreate it. So for this, Postgres does this. I don't know whether these guys, I don't think these guys ever put it actually in production. I think this paper came from CWI. In Postgres, they use deterministic seeds for the random function, so that if the same query shows up today versus tomorrow and it runs through the genetic algorithm, it'll produce the same result. Now, if you change the time, if you say like I'm going to run for a minute versus 30 seconds, then it may not produce the same result. But the idea is that you end up with the same thing. All right, so this is one approach. Yeah, sorry.
So in that case, it means like, let's say if the random time generated the worst possible scenario possible, it means it's going to be always that worst possible plan coming out of everything out and giving the same thing.
So his statement is, if you just have bad luck and your random algorithm picks the worst possible plan ever, and that no matter if you come back and try to run it again, you would end up with the exact same crappy plan. I don't know what you can do with Postgres. Actually, maybe I think in Postgres is you can override the seed. So you could say this is terrible. Try a new seed. Try it again. But then you just like roll. Set the slot machine. Just try it over again until you hope something works out. Yes.
Aren't there enough people complaining query optimizer in today's age for them to change this?
So his statement is, and he's correct, aren't there enough people complaining about Postgres Query Optimizer in today's age for someone to change it? Yes. Who's going to change it? Don't look at me. I want nothing to do with that. Yeah. So the Postgres code is beautiful. If you go look at it, it's well documented C code. It's pretty well structured. In some cases, like the documentation is like, hey, here's this algorithm implemented from this paper, and when you teach it, like it's. I haven't looked at a lot of enterprise code, but like it's the best I've ever seen. The optimizer, though, you put all the documentation you want, but like if the overall structure is just a rat's nest, which it is, because if then this, then that, right? My understanding is that we'll talk about Postgres in a second. My understanding from speaking to the developers that work on these things at Postgres or in Postgres, on Postgres, is that the optimizer is quite brittle, and that nobody wants to make any big changes because like there's a bunch of those latent or implicit assumptions about what the query plan is going to look like from one stage to the next. So if you violate something like them, up above, it'll break down below. Because again, like as I said, no one's sat down since the beginning of Postgres and said, okay, well, like here's all these advancements in query optimization that I realize we've been reading older papers, but here's one that's actually from 6 years ago that's modern. No one's really sat down and say, okay, here's how we actually should build this thing. At least and has gone about trying to do it. Yes?
Does the sampling function takes the precedence into account?
This question is, does the sampling function take precedence into account? So when you generate precedence mean like this thing has to be joined for this thing? No, there's no notion of that. It's more like, am I joining these two relations together? So I don't have an order in which I need to do the join. That's what the random choice is doing, right? Then I'm going to join A and B and then C and D, right? That it's picking that. The only thing that it knows is like because it can't pick like join A with D if there's not an edge between them, because it wouldn't be in the edge set when it does the random choice. So logically, it's making sure it's not choosing, again, Cartesian products, but it's not, there's no knowledge or information like, I need to join these two tables for these other two tables. It just randomly comes up with it. All right, so another technique from the late 80s was use simulated annealing. That was the hot thing in the 80s, right? And the idea of simulated annealing is you basically swap operators you generate some random query plan, and then you just sort of swap maybe the order of a join, right? So I have join AB, I'll just flip a coin, decide whether I want to swap AB to be BA. And then you check the cost of that new query plan. If it's less than the one the best you've seen so far, then you keep it and swap something else. If it isn't, then you reverse it back and then try again.
There's a whole bunch of math behind it.
What's that?
There's a whole bunch of math behind it.
There's a bunch of math behind it about bias coins and whatever, right? Like the advantage of this, you'll be able to break out of a local minimum, but again, it's a random walk. There's no guarantee you're going to end up with something that is good, right? They said if quantum computers become real, then you could do this. I can't say that because it's supposed to be anonymous, right? All right. Yeah. So again, we have all our we got to impose all the correctness guarantees we talked about before, but the properties and enforcement rules, right? So that we end up start moving things around in ways that we shouldn't. We need to reject it, right? Or set the cost in infinity, so you never include it. There's a paper on this. Nobody does this one. Okay, as we've been dancing around the Postgres story, right? So Postgres has this thing called the genetic algorithm, GEQO. And by default, it gets tripped on when the number of tables that you're referencing in your query is 13 or more, then this thing fires up. Anything less than that, they're using the system R styles join search. But anything above that, this switches on. And you can change that flag of when you actually want to enable it or just disable it entirely, right? So again, the idea is that you have a bunch of these rounds or generations. You generate a bunch of different variants of the query plan, and then you pick the ones, some subset of them that are going to have the lowest cost, and you're going to permute them or crossbreed them with other query plans, so that you end up with a bunch of new offspring of other query plans that are somehow inheriting the traits of the best query plans in the previous generation, and then you just repeat it over and over again until you end up with until you run out of time. So let's say that I'm joining 3 tables, R, S, and T, right? And so I just do randomly generate a bunch of different join orders, and here they're actually going to be picking maybe also what physical implementation I'm used for the joins, right? Either hash join or nested loop join, right? And then now for all of them, I'm going to generate some cost using my cost model that I have in my system, and then I'm going to anoint one or pick one that has the best cost, throw away the one with the lowest cost, and maybe I'll keep I'm showing three children or three entities per generation. You would have a lot more. Pick the one that maybe the top 2, and then pick a random portion of the query to change in some way, right? And then keep the rest, right? So in this case here, I decided to keep this nested loop with the S here, and I'll keep this. Where's the other one? Yeah, and then the hash join S and R. That's in there as well. But these are the traits getting populated over, and then everything else is going to get randomized. So again, the idea is that there's some trait, there's some join order or physical algorithm selection I did here in this first generation that caused me to have a good query plan. I don't know what it is, so I'm going to randomly pick something, and then I permute the rest, and then now in the second generation, I compute the cost all over again. If I have something that has the best cost than the one I've seen before, I choose that, throw away the one that has the highest cost, pick some trait that I want to keep around, and then do it again all over again, right? And keep doing this until you run out of time. And as he brought it before, to make sure that you don't, that if the same query I send in today and it runs through the optimizer, if I don't have a cache query plan or prepared statement, if I come back the next day and run the same query on the same data and same statistics, that I don't get a completely different query plan. They set the random seed deterministically so that you're guaranteed to be producing the same result from one day to the next. So why do this? Well, again, sometimes when the search gets really difficult, then randomly jumping around might be okay and help you get out of local minimums. The memory overhead is super cheap for all of this because all I'm doing is just flipping the coin and not keeping back the full search history of everything I've seen before, right? In the case of the paper guys read, they talked about how the DP table could get really, really big, and there was keeping track of the history of the changes you applied, and they had a bit set to keep track, minimal bit set to keep track of the history that you would need per entity in the DP table. Like there's a bunch of tricks they had to do to make sure the memory overhead didn't balloon up. In this random stuff, there's none of that because it's just so simple. As he brought up, to trace through this to figure out why something picked what it was going to pick is very, very difficult. And there's extra things to do to make sure that the query plans are deterministic. Did I take this out? 1 sec. I thought I had a screenshot I wanted to show. I did. Okay, perfect. So we had somebody a few years ago on the Postgres team come and talk about all the challenges and the things they're facing in the Postgres query optimizer, right? And in particular, he talks about how all the problems of the genetic algorithm, and like it doesn't scale. It actually isn't really entirely random. There's a bunch of limitations and assumptions they make to sort of simplify it, so it isn't truly maybe as random as we think it is. And then, as I said, like just go search Postgres bad query plans, and you'll see a bunch of people complaining about how this thing doesn't work. But again, this is so hard to do, and there's just nobody has been around to work on this. And it's if most of the queries are going to be 10 tables or less, they'll find the optimal ordering, assuming your stats are correct, but not always the case. But for the harder ones, you should not be running 100 table joins in Postgres. You want to be using like a data warehouse for those kind of things, right? All right, so to finish up, so we saw a bunch of different ideas, strategies, how to generate join orderings, and the idea that one of the main things we talked about is like, if I know the complexity of the query, then I want to choose a different approach, right? It seems sort of obvious, but most systems, most query optimizers are not implemented that way, right? And the German paper shows you, here's why you want to do this, and here's how to do it. It's pretty well. Another good thing to have in your bag of tricks, so whether you go in query optimization or databases or anything else the rest of your life in computer science, is the idea that when the problem's really super hard, right? There's all these divide and conquer approaches. There's all these, you can throw ML or AI stuff at it. But one trick that is actually a really good idea that would be useful for the rest of your life is the idea that I know if the problem is super intractable, then rather than just starting at a random location or just starting from nothing, if there's a quote unquote inferior algorithm that can at least approximate a good answer in a short amount of time, at least get me something better than I would have been without doing anything or random, then that's a good choice to make, because now you're at a good starting point where you're basically refining the solution you generate from the inferior algorithm to make it actually even better. And so that linearization of the IKKBZ technique he was doing, like those things aren't going to produce the true answer you want, but it's going to push you in the right direction. That's going to make things a lot easier for you. So not just query optimization, like in CS for a lot of things, this is a good idea. Okay? All right, so that's it for today. Next class, we're going to now do, so this was bottoms up joint enumeration. Now we're going to top down. The paper, like I said in the reading, isn't going to be adaptive, have an adaptive approach the way that the paper you guys read today is. So it's really like, okay, here's how to do enumeration in the context of a cascade style, volcano style file system. And then we'll also go over that dynamic hyperprogramming, dynamic programming hypergraph approach again, because the original paper they wrote was how to do this in a bottoms up system. But then the Thomas's German PhD advisor, he wrote another one how to do a top down system like cascades. So we'll go over that in more detail again as well. Okay? All right, guys, have a good weekend. See you.
Matter of fact, hold the cup. This is like that wood grain type of shit. Shout out to Blockhouse, my dogs. Catch one, Big Al, Mike Stroke, Gumbay, Randomized. I'm not the one who be amping up the weak ass rhymes. If you to spit, if it don't rip through your mind with the sweet anticipated, orchestrated punchline like a reverse the hands of time. Get you captivated quick with the bullshit. I keep the Cadillac equipped for the long trip. I got the remedy for bitches when they start shit. Surround sound like I make them hoes fuck quick and suck dick. Crown me as the third from the gutter. Shit, some niggas claiming never rapping is sudden. Don't push the button, yes you motherfuckers in front and you don't want nothing. If it did, it'll big start something.